So, so that was an example of an embedded system. Of course, the term embedded system is changing all the time. And so, what's an embedded system anyway? Well, it there's I think a couple ways to look at it, right? One is you can look at the system architecture or the structure of it and say, oh yeah, that's an embedded system. Another way is to say, well, it's more of a system that's devoted to a specific application. It's a specialized system, really meant for working well with a specific application, or maybe one or two. Okay, well, but I'd like to approach this more from the architecture. To me, it's one with a controller in the center and then a bunch of peripherals on the side. That's kind of the general flavor of what an embedded system is like. And you can build this controller many different ways. Some of you may have taken like digital design, may have learned VHDL, Verilog, and learned ways to use gates to build combinational logic, sequential logic, right? Many of you have done that, right? But that turns out to be only good for a small class of embedded systems, at least as far as I'm concerned. Because that's using what's called hardwired logic. Because you're thinking more in terms of hardware primitives. But most embedded systems, to me, really is built with a software controller. Okay, so you're using what's called a microcontroller, like what we saw earlier in the simulator, and we'll show you a few more. These are programmable, so you're essentially writing a program. I mean, not quite the same as the C programming you've learned from freshman year, and not a lot of times not really the general purpose program you write for a computer. Instead, you need to know the architecture, and then so that you can write code in a way that's meaningful to that architecture. Okay. Of course, there are many other people who like to think otherwise. They like to say, well, embedded programming should be more like more standardized. Should be more like, okay, you write it and then you need to abstract it so that it's more portable. So you change the architecture, the same program will work. Yeah, I mean, there are many other styles of doing it. But I think to learn it well, you should really start from just remove all the abstraction levels in between and just think the architecture and your program together. And eventually you can evolve into other ways that may suit the needs of your, say, the employer or somebody. But I think, yeah, so there's the controller at the center. And for this course, we're going to assume it's a microcontroller. That is, it's a microprocessor with an interfacing logic around it, built-in, memory built-in, so that it really minimizes the amount of logic you need between the controller and the device. It's more integrated and much more efficient this way. And peripherals are what we saw a little earlier, right? The LCDs, the buttons, keypads, maybe storage devices, your SD card, could be a radio for communication, could be Ethernet, right? A lot of these are all considered peripherals. And a trend in embedded systems or microcontrollers is that more and more of these peripherals are now being integrated on the same chip. So one chip today may used to be like 10 chips yesterday, or by yesterday I mean 10 years ago. And so we're seeing a larger scale integration all the time. And so the Bluetooth 4.0 board we'll be using includes one such system on chip. It's a single chip that has the radio on there, and that runs the Bluetooth 4.0 protocol stack. Has many other features all built in. So it's pretty powerful and low power at the same time. Because a lot of times once you start integrating everything on chip, you can better manage the power usage and then reduce the overall power consumption. That means longer battery life and everything. Okay, and another trend in embedded system, at least in the past 10 years or so, has been really going towards lower and lower power. Right, this wasn't the case like 30 years ago when like the 8051 architecture came out. But now people really pay attention to power efficiency and the energy management, and so that is something we hope to be able to do also with this Bluetooth 4.0 platform, really to show you some techniques that are really in use, the state-of-the-art techniques for extending your battery life. Okay, and that's part of what we hope to achieve in this course too, through these hands-on experience. I mean, this will be the second part of the course, not the first part. Okay, so how do you develop an embedded system? Well, yeah, you can start with hardware, make your own board. But I know this is a computer science department, and it's like, what? Make your own board? I like simulation, but no. Okay, so yeah, I mean, you could, and don't underestimate your own ability. But I guess I'm not asking you to make your own board in this course. Instead, you can use an existing board, and we'll show you some, and some built by our own lab. And so if you use an existing board, another way of calling an existing board is called a platform. It's meant for meant to be reusable. You don't have to reinvent a lot of the same features. Okay, so once you start with the hardware, then you can write software, or oftentimes called firmware, to run on this platform. Okay, and the steps involved are, well, really, in most cases, cross-compilation. And you know what that means, right? That means you compile on one machine, transfer the code to the board, and then run it on the separate board. That's what's called cross-compilation. When you learn programming, you probably didn't do cross-compilation because it's the same machine. It has the compiler, it has everything. You compile and A.out run or something, right? No, so that wouldn't be cross-compilation because it's the same machine that compiles and runs the code. In embedded systems, a little embedded board like this can't possibly have enough memory to store like GCC or any compiler that you might want. So it's done on a separate computer, a PC or whatever, compiled, and then take the code, transfer it over to the board. That's called the programming step. And then you run it. Okay, so that's the typical way it works. Now, but how do you get the program image onto this board? Well, there are other ways to do it, right? So you could either go through what's called a programmer. That's a separate board I didn't bring, but it could look just like this other one. So the program is sent to one board, and this board writes it to the memory of this other board. You could do it that way. Or if this already runs something called a bootloader, then you can just talk to it. And then it says, oh, I need to reprogram myself. Okay, takes the code, writes it into its own memory, reboot, and then, okay, that. Now, so you say, hey, so why don't we always do a bootloader? Well, that's because the very first time, there's nothing in there. It cannot program itself. It's empty. So the very first time, you got to put the bootloader on it. That's why the programmer is needed, right? Once the bootloader is in there, then it can program itself, okay? Of course, you have to be careful because the bootloader, if it writes over itself, then oops, you cannot do it again. So, so there are a couple of steps you need to be aware of. Anyway, so cross development looks like this. So you start with assembly or C. Okay, we'll make you play with assembly for a while just so that you're comfortable, and then after a while. Then once you get a good appreciation of what assembly is, then we let you program in C. And I'm actually developing a separate tool I don't know if it'll be ready. If it will be, it'll be the first time that you'll be using an even higher level tool to do programming. But okay, I'll try. It'll be fun. Okay. Well, but at least this is really the way standard way it's just done. The assembly file gets assembled by an assembler, of course, and that turns into sometimes binaries. Other times it's called a hex file. Most of the time you get a hex file. Hex file is really just the hex version of a binary file. It's mapped 1 to 1. And then through a programmer, which oftentimes looks like a box like that, then it writes into the program memory of the little board there. Or if you have a bootloader, you can skip the programmer step and then go straight to the board. Okay, and then in this course, we'll start you out with SDCC, which is a free open source compiler. It's really, the whole name is a Small Device C Compiler, SDCC. And you can download it. Let me just Google it, and you can download it and you try to install it on your own machine. And it's pretty cool in that it generates code for everything that GCC doesn't support. So GCC supports a bunch of, well, 32-bit, 64-bit, maybe some 16-bit, but then when it goes down to 8-bit, okay, maybe there's 1 or 2 ISAs that GCC supports. SDCs is kind of this you poor little processor, nobody's wants you, huh? Okay, so I'll generate code for you. Okay, so it covers a bunch of weird architectures, and 8051 is one some people might call weird architectures, and you'll see because it's fun to program. I like programming in 8051 assembly myself. It's probably the most fun of any assembly I've had. Because like ARM, you might say, hey, but ARM is more cool, right? Everything uses ARM now. Well, ARM assembly is really not meant for humans to write. It's just awful to program. It's I think 8051 is a much nicer assembly language to be programming in. It's actually usable. You don't have to think very much, and it does the right thing. Anyway, so SDCC is what we'll be using for you to be writing some of the later programs in the simulator part. And if you want to develop for the Bluetooth 4.0 board, and well, you could use SDCC, but it doesn't have a way to link in the Bluetooth protocol stack. And you know why you need a protocol stack, right? Because without the protocol stack, you can't talk correctly with your smartphone or your computer or something, right? So the software part decides how the communication actually works from the media access and up. Without software stack, it's just an 8051 with a generic radio. If for now we haven't been able to make that or decouple SDCC from the Bluetooth 4.0 stack. That's the way the company, Texas Instruments, has set it up to work. And the reason is they want to protect their intellectual property. They don't want just anybody to be able to, or any other company to take their protocol stack, which actually is very difficult to write, and use it on somebody else's chip. But we're working on ways so that you can use a different compiler rather than IAR. Well, we'll see how that's going to work out. Okay, so.